Artificial Neural Networks, ANN. Artificial neural networks and deep learning, which we will talk about it later on, are among the most advanced machine learning and artificial intelligence tools successfully applied in many interesting applications, including smart speakers such as Google Assistant, Alexa, and Siri, and also self-driving cars, image recognition, and a lot of other interesting applications. ANN imitates how neurons in our brains work. This is a single neuron. How many neurons do you think our brains have? Try to take a guess. Well, an average human brain has about 86 billion neurons. That's right, billions with B, 86 billion neurons. Our brains contains and interconnected networks, billions of them, of neurons that process all the information that we get through all of our senses. ANN try to imitate this process. Computers and the brain, a contrast. If there was a fight possible between a computer and the brain, which one do you think it would win? Let's see some facts. In arithmetic, the power of brain is no match for a computer. In fact, the power of a pocket calculator is 10 times the power of a brain. So the computer would win in arithmetic, big time. On the other hand, in vision, the power of brain is more than 1,000 of supercomputers. So a brain would win. In terms of memory of arbitrary details, computer would win. In terms of memory of real-world facts, the brain would win. A computer must be programmed explicitly. You need to tell it what exactly it should do. On the other hand, the brain can learn through experiences. More on artificial neural networks. Early works on ANN started in 1950s through 1960s. There have been many research and development on ANN. In fact, at the time of this lecture being recorded, there have been more than 500 of books and 20 journals dedicated to ANN. Learning ANN in details would require its own course, and there is just so much that we can talk about it here. So we're going to be brief. An example of artificial neural network is a perceptron. A perceptron is basically a sequence of connected nodes, aka a network. Each set of nodes at each step is called a layer. The first layer is the set of feature variables. You can think of these different layers as a set of tweaks and knobs that you can adjust and manipulate to configure the relationship between the input variables and the target variable. Mathematically, you can think of these layers as different functions. The output of each function or layer is the input of the next one until the very last where we actually make our prediction for the target variable. The role of each step or each layer is when add up, each differently work on different aspects of the data or the problem, but when add up, it would help us to find the relationship between feature variables and target variable. For example, in classification or classifying a set of fruits, we can think of it as different layers at different features. For example, texture, color, shape, size. that when add up, it would help us to distinguish or classify different fruits. This is just for illustration. Of course, this is too dumb to be true. Let's go ahead and see an example of a neuron here you see here, but I want to show you an example of a perceptron here. So this is a schematic view of a Rosenblatt perceptron. As you see here, this is just a network that includes nodes or these little circles. These little circles in artificial neural networks is called neurons. This is the first layer, which is basically the feature variables. We can have multiple layers or we can have just a single layer perceptron. We will talk about these later on, but you need to know that in perceptrons, we use what is called as activation function for determining the output of each layers or neurons in each layer, which are called units. We will talk about this more. How artificial neural networks work. To answer this question, let's go back a little. Remember how a linear regression model works? It is just a sum product of independent variables, x's, and their coefficients or weights, shown by w's, which would render the predicted value of the dependent variable y. B hat here is just the intercept. Let's be a little creative here and rearrange this formula to this shape, for example. So we have put the independent variables into these little boxes and their coefficients or weights on the arrows that comes out of these boxes. This is just a rearrangement. If you multiply the values in the boxes by the coefficients that are on the arrows, it would give us the same formula that we have above. Suppose this continues to xn by wn. All right, now let's go one step further and get a little bit more complicated. Let's see the logistic regression model. The logistic regression is similar, except that it has an additional step, the sigmoid or the logistic function. Now, let's try to do the same representation for the logistic regression. So we're going to put the independent variables into these little boxes and then their coefficients onto the arrows that comes out of them. And then we have to add an extra step. The sigmoid function between the arrows, the multiplication or sum product, and the y value, the predicted y value. This sigmoid function or the logistic function, its role is just to convert the value that comes out of the sum product of independent variables and the coefficients w's into a value between 0 and 1. Not difficult to understand, huh? Well, congratulations, you just understood a version of a neural networks. A logistic regression can actually be viewed as a single layer perceptron, which is a neural network. A neural network is just a multi-layer perceptron. So consider these as one layer. If you had more layers between these sum products and the y's, it would be called a multi-layer perceptron. So logistic regression is just a single layer perceptron. Multi-layers perceptrons. A multi-layer perceptrons take a step further from the idea in logistic regression by adding hidden layers in between. The neurons, which are the boxes in the hidden layers, are called hidden units. Each hidden unit computes a nonlinear function of the weighted sum of the input features, resulting in intermediate outputs VIs that are used in the prediction of the dependent variable y. So this is a multi-layer perceptrons, which is similar to what we had, somehow similar to what we had for the logistic regression, for example, as you see here. So the first layer here is the input features. Input features, the first layer also for the logistic regression. In the logistic regression, between predicting the value of y and our input features, we had this function. In the multi-layer perceptron, instead of this function, we actually have hidden layers. So these hidden layers act as a function that's going to help to find a relationship between the input features and the predicted value or the dependent variable y. During the training process, when we have data points to train the algorithm, suppose we have all the x feature values, and based on these feature values, we want to predict the value of y, the dependent variable. So what's going to happen is each value in these neurons are going to be multiplied by these coefficients or weights on the arrows that comes out of them, and that sum product is going to be inputs to the next layers, which here are the hidden layers. These boxes, which are neurons in the hidden layers, are called hidden units. These hidden units are actually functions. An example of this function can be seen here. These are called activation function. This one, hi, is a tangent h function. So what it does is it takes the output or the input that we get from the previous layers, and it's going to produce a value, the intermediate values here. These values then are going to be used in making the prediction of value of the dependent variable y. So a multi-layer perceptron is somehow similar to a single layer perceptron, which is the logistic regression, except it has multiple layers in between. And each unit or each neurons act as a function, which is an activation function. All of this is actually to help find the value of the dependent variable or to predict it. This act of feeding in these values and then multiply them and then give it to the next layer and then next layer and etc. This is called forward propagation. So here we see a simple neural network which we only have one layers here. And if you add more hidden layers, the neural network is going to be called deep neural network or deep learning. This is what deep learning is. Deep learning is artificial neural networks with multiple hidden layers. So a deep learning neural network is just a more complicated with more added hidden layers neural networks. How learning works in multi-layers perceptrons. With forward propagation, the artificial neural networks, the multi-layer perceptrons, estimated the output variable y based on the input variables, the feature variable x's, using the estimated values of coefficients or the weights in the hidden layers as well as those in the arrows. So suppose we want to train our multi-layer perceptrons. So we're going to use our training data. For the training data, we have the feature variable x as well as the target variable y. The feature variable x here, as shown by capital, is actually an array of different values for each feature. x1 for feature 1, x2 for feature 2, and so on and so forth. Suppose we have n features, so xn. So what we're going to do is we're going to feed in these values, the training data, into specifically the x variable, the feature variable, into the multi-layer perceptrons. So these values are going to be the values in the first layer, and they're going to feed in, multiply, and go to the next layer and next layer and next layer during what is called as forward propagation. So that at the end in the right, we're going to get the predicted value y hat here. But this is a predicted value, and it's usually wrong. It means that it's going to be different from the actual value here. So we can compute the error. During the training process, what we are looking for is to minimize the errors that we have. We're going to do this by a process that is called back propagation. In the back propagation, we're going to actually modify and adjust the coefficients or the weights values in the hidden layers and on the arrows. To minimize the error, when given the output y, it adjusts the coefficients or weights in the hidden layer or in the hidden layers in backward propagation. This learning process is repeated until the error is minimized. To find the optimal weights, optimization algorithms such as the gradient descent and optimization solver method are used. Learning the weights in artificial neural networks can actually take a lot of time and a lot of memory when applying the artificial neural network algorithm. So you have to be careful during the learning process to not make it too time consuming, as well as it can actually end up having, if you add more layers and make your algorithm more complex, it's going to increase the possibility of overfitting. Activation function. As mentioned earlier, the hidden units in the hidden layers actually include a function which is called activation function. These activation functions are used to compute the intermediate values here, which are then later used to compute the predicted value of the dependent variable y. There are a variety of activation functions that we can use. Here is a list of them. If you don't know what activation function to use, start with ReLo. ReLo is short for rectified linear unit. And then experiment with other functions and pick whichever gives you the faster and better results. Playing with an artificial neural network in your browser. There is this cool website, it's called Neural Network Playground, that we can see and play with a neural network algorithm, actually a multi-layer perceptrons. So as you see here, there are different features in this website that you can actually play with. You can play with all the parameters, all the features, add features, remove features, add layers or remove layers, also neurons, add neurons or remove neurons, and also solve for different types of problems. So to look for the website, search for Playground TensorFlow. And the first website, it's called a neural network playground. If you click on it, it's going to come to this website. So this website is, as its name suggests, it's a playground, it's a simulation. It's not a simulation actually, it's just a representation of a neural network's very cool design that you can play with it. On the left side, we have the data. You can pick actually from these 4 types of data here. These data points here, this is for a classification problems. The data points that are shown in the orange are actually the -1 class, and the blue dot points are the positive class here. So you have these 4 choices here that you can play. Which one do you want to use? Which problem do you want to use? The next one is the ratio of training. This is like the train test split, how much of your data you want to have for testing and training. So for example, 50-50%, 60-40, 70% for training, 30% for testing. And forget about these last 2. Then here, this is actually the feature layer. So we have x1 and x2, only we have 2 features here, but you can also add more features. For example, x1 is square, x2 is square, x1 multiplied by x2, and etc. This is the hidden layers here. So you can also play with this. You can actually add neurons or remove neurons to this. You can actually add or remove layers here. So more layers, less layers. You can play with this, but you have to know that adding more layers or neurons is going to make your model complicated, more complex. And you have to be careful about that, because not only it's going to increase your training process, time, and memory, it can also make your model susceptible to overfitting. Right, so let's go ahead here, and you can also actually, for the last layer here, you can also add and remove neurons here. So let's go ahead and run this algorithm. Also, if you look at this here, you can change the values for the learning rate and also the activation function. You can use reload, the tanh, the sigmoid, or the logistic function, and also the linear function. The default is reload, and then whether you want to use regularization or not, and the regularization rate, and whether you want to do a classification problem or a regression problem. So let's, as it is, let's go ahead and run this to see what's going to happen. So you can see that the decision boundaries to classify these 2 different classes from each other is building up smoothly and gradually. You can try this with different features or different setting and dynamics, and also on different data problems. So go ahead and open your browser and try it out yourself. The impact of hidden units or neurons. Generally, adding more hidden units and also hidden layers would add to the complexity of neural networks. Let's see an example. Here, there is 3 models: a single hidden layer neural network with 1 hidden unit, 10 hidden units, and 100 hidden units. A single hidden layer neural network mathematically is equivalent to logistic regression. Let's see the examples. So we have 3 neural networks here for a classification problem. The first one on the left is a 1 unit, 1 layer neural networks. It is a simple model that is incapable of identifying sophisticated and complicated relationship between data. This model would likely to suffer from underfitting problem. The second model in the middle is a 1 layer, 10 units neural network. By adding more units, we're going to make the model more complex and enabling it to recognize more complex relationships. So as you see here, the contours, the segregation lines are getting more sophisticated. And on the right, we have an example of a 1 layer, 100 units neural networks. which is even more complicated than the model in the middle because we have added more hidden units. Artificial neural networks and specifically multi-layer perceptrons in Scikit-Learn. So here I want to show you how we can actually develop a multi-layer perceptrons in Scikit-Learn. Suppose we want to build a two hidden layer perceptrons. So we're going to call the MLP classifier, which is in the neural networks module in Scikit-Learn. And then we're going to build a copy of that, and we can specify the parameters of the model, including the hidden layers sizes. So here we want to build a two-layer perceptrons. So that's why we have, this is the number of the number of units in the first layer, or the number of neurons, and this is the number of neurons in the second layer. And also to solve the optimization problem, when we are training our algorithm, we need to use a solver. So the default is LFBGS, but there are other options that we can use. There are actually a lot of other parameters that we can tune to improve the performance of the model. One layer perceptron versus two layers perceptron. Adding more hidden layers would make more complex models. However, that could also increase computation and memory usage and the risk of overfitting. We learn how to build a multi-layer perceptron in Scikit-Learn, specifically a two hidden layer perceptron, as we see here. Let's now make a comparison between a one-layer perceptron in classification versus a two-layer perceptron. So here on the left, we have a one-layer perceptron with 10 units in the layer that is trying to classify this classification problem. On the right, we have a two hidden layer perceptron with 10 hidden units in each layer. The model on the right is more complex and therefore potentially is more capable of identifying more complex relationships. Regularization of MLP. To avoid overfitting of multi-layer perceptrons, we can use L2 regularization with parameter alpha. Larger values of alpha would enforce more regularization. We can do this during the process when we define our model. We can set the values of alpha. Let's see an example for setting different values for alpha, which is regularization. The model on the left, alpha is 1%. If you look at the accuracy score for the trained data, it's 97%. For test data, it's 72%. So apparently, this model suffers from overfitting. If we increase alpha to 5 instead, we get the model on the right. The accuracy score for this model on the trained data is 87%, and for the test data is 92%. So we actually resolved the overfitting problem by enforcing regularization on this model. Regularization would become more necessary when you build more complex models, especially by adding more hidden units and hidden layers.